Okay, so what I'm going to show you is I'm going to show you what we're going to do with the first acid-base titration activity in the write-up. I'm going to walk you through the types of calculations I want us to be able to do. Understand the reason for these titrations is we're going to have to visualize our acid-base equilibrium and titration problems as curves. If we can start thinking of our problems as along these curves, then it'll go a long way to help us solve more complex problems. We started our first week doing the problems without thinking about how the curves look and how they work, and there's a lot of information here. And what we're going to do is we're going to be able to look at these curves and predict the points on them. Theoretically, every point on this curve, okay, we could actually predict with our pencil and paper math, okay, based on our understanding of acid-base chemistry. Now, there's some things we're going to do here. We're going to figure out the initial pH, a point along this line somewhere, the equivalence point, and the end point. And we're going to calculate those pHs and compare them to the parts of the curve. We're also going to figure out the concentration of the acid, okay, through a couple different ways. Okay, and we're going to basically understand these curves in detail. The first thing to notice is that this is a strong acid, strong base titration. And on the website, I have your files there so that you can pull them up. If you don't have them on your computer yet, you can download them from the website under today's lesson, and you can manipulate them. It's nice to be able to hit examine. I'm doing analyze, and I'm hitting examine, which is checked, and I'm dragging across. And if you notice, I'm able to drag and read. Every point gives me a different pH, and we did a milliliter. So our curves won't be perfect because we're doing a milliliter at a time. Okay, but certainly we get a lot of information. It's a fast way to do it. Some people will do this as a drip method. It takes much, much longer. So in any case, getting started, the first thing to realize, this is a strong acid, strong base titration. And the first thing I want us to notice is we should be able to figure out the endpoint pretty quickly. Now, the endpoint is going to be the middle of this kind of tangent line. All right. Now, we don't really have to guess too much because when it comes to strong acid, strong base, okay, the neutralization point is always going to be 7. Okay, I can't say that enough. Why? Because the strong acid, strong base has no conjugate acid or conjugate base that can go in the reverse to create a pH other than 7. Once we neutralize all of our H pluses and our hydroxides, okay, we have what we call equivalence. And it's always going to be 7, but only for strong acid, strong base. It's very important you understand that. So the closest point I see here is at 51 at 7.39, which means somewhere in between 51, okay, and 50 is our equivalence point, okay? And we're just going to use 51. So I am going to just use 51 because it's the closest point I have, but you know, it's between 50 and 51 somewhere. And that kind of makes a lot of sense as we're going to talk about that soon. Okay, so the equivalence point is at 7 definitely. So we get 51 milliliters approximately. As if you can read the upper right-hand corner here, as I get to 51, it's about 7. In truth, it's a little lower, but that's okay. Now, if you notice your endpoint, I'm picking the equivalence point at 7, which is a little lower than what we have here, but it's good enough for the work we're going to do here. The equivalence point is the point where the H pluses equal the hydroxides, okay? And I'm going to go to another place where I can annotate on here, but you may want to keep yours open to manipulate to see where these points exist. So let me just go to a place where I'm going to annotate. Okay, so I have this equivalence point at 51. I know it's not perfect, it's a little less, but we'll say 51 is my equivalence point. It's about a pH of 7. Okay, and that's because it's a strong acid, strong base titration. Only in that scenario. When you have a weak acid or a weak base involved, that'll never be 7 because of the conjugate acids and bases that are made that have some ability to recreate the acid or the base, as we'll talk about in the second curve we'll get to in class tomorrow. Okay, so our equivalent point is 51. So the first thing we're going to do is we're going to walk ourselves along this curve and talk about the different points in the mathematics. The first thing I want to do is initial pH. Looking at this point here, what is initial pH? Well, without adding any base, we added 25 milliliters. I'm sorry, we start with 25 milliliters of well, we didn't know the concentration. 25 milliliters of some unknown concentration of HCl. And we want to figure that out. So there's many ways we can do this. Let's start with the first method. The first method is I'm going to use my equivalence. I know that 51 milliliters of base, because we're looking at sodium hydroxide. This is the volume of base that's added. Okay, so I have 51 milliliters of sodium hydroxide that was added till I got to the equivalence point. So this is the equivalence point. All right, now, in order to figure out, okay, the initial pH, now I know that the pH is listed here, but what I need to know is, does this graph coincide with what I know? So we're going to try to recreate this graph given the experimental data and verify it with pencil and paper. So we're going to try to find the initial pH and see if it comes close to what we have here based on the concentration of the acid, which we don't know. So the first step is, let's go find the concentration of the acid. Now I do so by looking at my equivalence point. Now at this equivalence point, we should be very clear here. Stoichiometrically, all of the H pluses that were in the beaker equal the hydroxides that were added. That's at this point here. Okay, so that means if I can figure out the moles of sodium hydroxide that was added, right, it's NaOH added, then that's the moles of my H plus. And if I know the total, or I know the volume of my initial solution, this is getting pretty easy when you think about it. So I take my 51 milliliters of NaOH. Let's start down here. And the first thing I'm going to do is I'm going to divide by 1,000 milliliters for 1 liter. And this is going to give me a liter. And the reason why I'm doing that is because, well, if I know the volume and I know the molarity, I can get the moles. So you don't have to do it as fancy as this, but for every 1 liter, okay, I had the base that was being added was 0.05 molar. That was the base, the standardized base being added. Okay, if you didn't know that, now you do. So 0.05 molar base was added, so 0.05 moles for every 1 liter. And this will give me the total moles of hydroxide, which, if you want to do it even further, okay, 1 hydroxide is equal to 1 H plus. Now, Mr. Grotsky, why am I even bothering to do that? I do that because sometimes bases could be basic, have 2 hydroxides, and sometimes the acids could be diprotic. So it's just a good way to keep track of H's and OH's. This will always be 1 to 1. Now, what I am assuming is that 1 sodium hydroxide gives me 1 hydroxide. So in truth, I probably should have, before this, just to make things neat and understandable, for every 1 NaOH, there's 1 OH minus. Now, again, you don't have to if you see that, but that probably should be in there, okay, to understand that it's a 1 to 1 in that case, because this right here is always the case. Any case, that's going to give me moles of my H pluses. Now, once I have moles of H pluses, okay, what am I going to do with that? Well, I'm going to divide by the volume that's in the beaker, and that's 0.025, okay, liters. And this, my friends, will give me the concentration of my acid that I started with. Is one of the things you had to figure out. The whole point, one of the points of a titration is to figure out the concentration of your unknown acid. So this will give me a concentration of my acid, which I'll get for you in a second. But this method is a little different than what you did last year, although we could use the same method. Let's go find that number. So very simply, okay, 51 divided by 1,000, 0.051, okay, times 0.05, okay, so I get 0.00255 moles. So this mole down here is, let's put it in blue because I can, 0.00255 as my moles. Divide that by 0.025, and I get the acid concentration is 0.102 molar. That's good for me because I tried to make 0.10 molar, so not too bad. Okay, good for me. So my initial concentration of my acid, HCl, is equal to 0.102 molar. Now, I could have done it another way. The other way I could have done it was old school method. Hey, MV of the acid equals MV of the base. Now, careful with MV of the acid equals MV of the base, because this is a potential disaster if your acid and base are not monobasic and monoprotic. And these are 1-to-1. One HCl gives off one proton, and one NaOH is one hydroxide. If they're not, you have to make some adjustments. That's why this is a little dangerous, but it works out. So the molarity of the acid was our unknown. The volume was 25 milliliters. And the molarity of our base, okay, was known to be 0.05 molar, and this is how we did it last year. The volume that we added to get the equivalence, okay, we added how much? We added 51. So you had to use that value, okay, here. All right. I've used it over here to get total moles. Same thing, because molarity times volume is moles equals moles. I mean, that's the same thing that we're doing here. So in any case, 0.05 times 51, divide by 0.25, and you should get, sorry, that's 25 milliliters, right? So that's not 0.25. So 0.05 molar times 51, divide by 25 milliliters, and I get the same answer. My molarity, okay, of my acid is 0.102. It's the same thing. Okay, this is fraught with danger though, because you could have a diprotic and a monoprotic, and this 1-to-1 won't work. Okay, unless you make some changes over here, and we'll go over that some other time. All right, so cool beans. Moving on. So let's get rid of this. Now we have our initial concentration to be 0.12 molar. Let's see if we can validate that with the pH that we're supposed to get. If it's 0.102 molar, okay, how can I find the initial pH? Well, if it's hydrochloric acid is a strong acid, which means your 0.102 molar for the acid is equal to 0.102 molar for the H+, because there's complete dissociation. There's no equilibrium problem here. Strong acid, strong base stuff is complete stoichiometry. There is no equilibrium here. It's direct one-way completion reactions. So if I've got 0.102 molar H pluses, heck, I want to do negative log. Negative log of that. Okay, so negative log of 0.102 molar, and I get something that makes, I get a pH to be 0.991. That doesn't feel right. Okay, initial pH of less than 1. Let me just make sure I did that right. So negative log of 0.102. Yeah, and of course that's what I get, something less than 1. All right, now what did we get on the actual one? So going back to the logger profile and still using the examine key, when there was 0 milliliters, the pH was 0.077. So certainly not the same value, and there could be many reasons for that. I mean, I calibrated the pH probes, but only with 1 point calibration, so that could be the difference. But it isn't so far-fetched. 0.77 is close to the 0.99 that I got. So there's definitely some comparison here. Of course, ours is going to be theoretical, and this is the experiment, and all the errors in between. So there is some definite relationship here. 0.99, 0.77, I'll take it. Okay, So we've got the initial pH, we've got the equivalence point marked, okay, right here. We have the initial pH, and now let's pick a point that's somewhere in between, okay? Let's go pick this point, okay? And this point, if this is 51, this is 50, 49, okay, 48, 47, 46, 45, 44, 43, 42, 41. This is 41 milliliters, assuming I didn't make any mistakes. Okay, so let's see if we can find that pH. Now, how in the world will we figure out a point and verify that point? Because sincerely, you should be able to build this entire chart theoretically and have some comparison to our experiment. All right, let's get some room here. All right, and let's get some of this stuff out of the way. And all right, now, how am I going to do that? Of course, I just erased my line. So let's go find it again. Oh, there it is. Bad Grotsky, good pizza. Now, let's get rid of some of this. All right, now, how am I going to do that? Well, actually, it's very easy. There's no stoichiometry here. Why isn't there? Because it's just complete annihilation of a base to an acid with no conjugate acids or bases produced that do anything with water. The conjugate acids produced is Cl negative, which doesn't ionize water, and Na plus. Both of these are the byproducts of the reaction. They don't do anything with water. So the only thing I have to deal with is the H plus and the OH minus. So at 41 milliliters of base added, question is, what's the pH? Well, I have 41 milliliters of base added to, well, how much acid? Well, there's 25 milliliters of acid. So what I'm going to have to do here is I'm going to have to, all right, figure out how many moles. So I'm going to do, let's do this in red here. I'm going to take my 41 milliliters, same thing, divide by 1,000. I know you can do this a faster way, but I'm just showing it out. And for every 1 liter, there's the concentration of the base to be 0.05. That's what we started with. Okay, and that'll give me moles. Now let's do the same thing for the acid. 25 milliliters. I'm dividing by 1,000. And I'm timesing that by my known concentration, which is in this case, 1 liter is 0.102. I'll use exactly what we find here. Okay, let's find moles of each. So 41 milliliters, divide by 1,000. Turn your calculator on first. I probably could have done that in my head. Times 0.05, and I get 0.00205 moles of what? Of base. Okay, and I get, for the acid, I get 0.00255. Moles of acid. All right, so 0.00, was that 205? Christmas in July. Can't read my own handwriting. So let's do this, make sure I get it right. Yeah, 205. I know you were screaming, yes, Grotsky, don't waste your time. Okay, so, well, we have a lot more acid than base, but the acid totally annihilates the base. So I can actually subtract these two, right? We're going to lose minus. If you want to do you actually do a stoich table here if you wanted to, because in titration there's always stoichiometry involved to the equivalence point. Okay, in this case there's always stoichiometry because it's strong acid, strong base. So I can do my acid and my base, okay, and I know my acid is 0.00255. My base is 0.00205, and of course the limiting factor is the base, so you minus that value, and you minus that same value. So there's your initial, there's your change, and of course 0.00255 minus 0.00205, okay, gives me the amount of what's left over, of course the acid left over, okay, 5 times 10 to the negative 4, or 0.00005, okay, that's the moles of acid that remain at that position. And that's important. What do I do with it? I'm trying to find a concentration. Okay? If I want a concentration, but if I want to know what the pH is at 41 milliliters, I have the moles of acid, which we all know, party people, is the moles of what? The moles of H+. So let's do a negative log of that. It's just that simple. Now hold on, I'm sorry. I have to make that a concentration first. Bad Grotsky. Getting ahead of myself. So let's take the moles of this. Let's divide by the volume it's in. And this is important, very important, because at this point, we're going to use total volume, right? We have 41 milliliters of base added, plus we have what? 25 milliliters. And of course, that has to be 0.0 if we're doing liters on the bottom. Okay, so 5 times 10 negative 4 divided by, okay, 0.041 plus 0.025, converting to liters. Might have to use a total volume. And this gives me, okay, and I have a lot of stuff going on here, so just going to get rid of some stuff. So this gives me, okay, 0.00757 molar for 41 milliliters of base added to the total volume, okay, that's 66. All right, so we're going to take this and do a negative log of that to find the what, because this is the molarity of the acid, which is the molarity of the proton because it's a strong acid. So again, no equilibrium here, guys. Nothing. There's no equilibrium questions whatsoever in this type of problem. It's important you realize this, and components of this problem are in other problems. 757, new negative log, I can do this. Negative log of 0.00757. And I get a pH to be equal to 2.12. So that pH is what should be at 41. We were at what? 0.99, and now we're at what? 2.12. Not much of a change. It's not changing much. Now this is not a buffer. Okay, I'm going to explain why this doesn't change much in a little while. Okay, let's go see what we get for that point on 41. Okay, so we're back at it here with the logger profile, and if you go to 41, if that in fact was where I was, okay, I get 1.8 as the experimental, and we're supposed to get what, 2.0? Okay, so nothing crazy there. Again, the experiment is somewhat showing what the theoretical would be. Okay, 2.12, 1.8, not too far away, but this isn't increasing that much. It's a really fast incline. Look at the spaces in between the points here. And why do they increase so fast? Well, I'm going to explain that tomorrow if you don't know that, but I want to get to the last point since this lecture is getting lengthy. We have the equivalence point. I want to find this last point. Okay, 51, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So what's the pH right here? What's the pH right there? That last point. Okay, let's clean some stuff up. How do I do that? Well, that's the easiest thing of all. At the equivalence point, okay, we have 51 milliliters, right, of base that was added. Now we figured out that that annihilated all the acid. So at this point, okay, at this point, below 7, okay, I really don't need any information except total volume. At this point, And again, I have to count again because I have my short-term memory is going. 52, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So 15 on top of my 51, right? Did I do that right? I don't know. We'll make it up. 66. So this is 66, we'll say. And if it's not, we'll pretend. Okay, now, so 66 milliliters of base added, but that's also with what? 25 milliliters. So to figure out this pH, I'm going to need a concentration of my hydroxide. Now, the molarity of my hydroxide, total volume, is going to be 25 plus 66. So that's going to be what, my 91 there? I can do this. Yeah, 65 is 11, so 91 milliliters, so 0.091 liters. Now I need a concentration of my hydroxide. Since it's a strong base, concentration hydroxide, concentration will work out fine. Okay, now, my question is, to find this outermost pH, all I need to know is how much extra hydroxides I've added since the equivalence. So at this point here, guys, all the hydroxide's been eaten up. And of course, all the acid has been. So how many moles do I have beyond this point? So from this point forward, okay, how much hydroxide has been added? Well, that's easy. We counted up what? 16? 16 milliliters. 16 milliliters beyond the equivalence point has been added, if I hit it correctly, of NaOH. All I've got to do is figure out that concentration, or how many moles. So 16 again, divide by 1,000 milliliters. That's a liter. Last thing I'm going to do is get rid of the liter. I know the concentration is 0.05 what moles. Let's go find those moles. 16 divide by 1,000. Okay, times 0.05. And that gives me 8 times 10 to the negative 4 moles of NaOH has been added. Okay, now to find a concentration, I'm going to put that over the total volume again. Can't say enough. Another place where we use the total volume. So I'm going to divide that by 0.091, and I get a molarity to be, okay, equal to 0.00879. That's the concentration of my hydroxide. All right, now what do I do with that? Well, I'm trying to find a pH that matches that, right? So I'll do negative log. Okay, so negative log of 0.00879. And I get a pOH. Don't lose track what you just found. Negative log of the hydroxide is a pOH equal to 2.05. 14 minus that gives me the pOH, right? And I get a pH, once I subtract 14 from that, of 11.94, 11.9. That's my pH at that position. All right. And again, the trick behind this was to realize that once you have neutralization, all we needed was data above the equivalence point, and all I was adding was hydroxides. So essentially I was adding hydroxides to an ever increasing volume and the pH. Now notice it's flattening out. The reason why it's flattening out, it's trying to achieve the concentration or the pH of a pure 0.05 molar solution. As you add 1,000 more milliliters, this will approach but never quite get to whatever the pH of 0.05 molar of NaOH is. That's why it flattens out. Okay, this solution becomes more dilute and more dilute in terms of the water. And okay, any case, moving on. And that's basically it. Let's go see if 11.9 was the final one there. I don't know. Okay, it should make some sense. And we get 11.93. So we were able to predict and validate most of these points, and that's what we're going to do with these curves. All right. So so everything that we did there, I would like to see on the the work, the printed copy, all your work, everything we just did there, those points that we did. I want to see the work there for lab activity. Okay, done.